So chapter 3 is ideal gas. 3.1, the Avogadro Constant. So Avogadro Constant, you should know, it is 6.02 times 10 to the power of 23. So you have to know the meaning of this number. So they said Avogadro Constant, Na, the number of atoms present in 12 grams of carbon 12. So in 12 grams of carbon 12, it contains this amount of atoms. So this 12 grams of carbon 12 is actually 1 mole in chemistry. So 1 mole of carbon 12 contains this amount of atoms. Okay, so that's why 1 mole is introduced here. A mole, amount of substance containing same number of particles as in 12 grams of carbon 12. So chemistry. So let's move on. 3.2, equation of state. Equation of state. So PV equal to nRT. No? So let's see. Ideal gas. Ideal gas. Ideal gas means perfect gas. The word ideal means perfect. Perfect gas. Gas which obey the ideal gas equations for all values of P, V, and T. So the ideal gas equation is PV equal to nRT. So P stands for pressure, should be capital P, capital P stands for pressure. V stands for volume, N mole, R is 8.31, it's a constant, 8.31. Okay, let's write down here. R is 8.31. T is temperature in Kelvin. Temperature in Kelvin. So T is temperature in Kelvin. Okay, so that means you have to add 273. No? You have to add 273 to degrees Celsius. So which is temperature in degrees Celsius plus 273. Okay, plus 273. Then you will get temperature in Kelvin. When we talk about pressure, we need to know there are many kinds of units for pressure. For example, pressure can be Pascal, pressure can be Newton force over area, Newton per meter square. Pressure, you can use cmHg also, okay, or mmHg and so on. So there are so many kind of units for pressure. Sometimes you can also see like mmHg, or maybe kilopascal, or maybe atm, atmospheric pressure. So 1 atm, those kind of units. So there are so many kind of so many ways to talk about pressures in different units. So which unit should we take? It is fixed actually. You take Pascal. Okay, you take Pascal, and your volume must match accordingly. Your volume must use meter cube. So this is what we call the SI unit, Pascal and meter cube, the SI unit. And then sometimes you can use kilopascal, which match with dm cube. This is okay also. Okay also. So either the first pair or the second pair is up to you to decide. Okay, so only these two situations. If you want to use other unit of pressure, like ATM or whatever other unit, then your R must be other value already. We, in our Cambridge syllabus, we just focus on R equal to 8.31. So the pressure and volume must match accordingly. Basically follow SI unit. So Next point. Conditions for equation to be valid, we must have fixed amount of gas. That means your n, n is the number of mole, right? So your n must be same throughout the whole experiments. Okay, so must be ideal gas also. Ideal gas. Okay, so for example, let's say if your container has gas released to the surrounding, then you can't use PV equal to nRT anymore because the gas decrease in terms of number of mole. So the mole is not fixed anymore, and we can't use PV equal to nRT. Okay, so that is example where we can't use when gas leaking happen. Now, Boyle's law. Boyle's law. Boyle's law is where they said the the pressure is inversely proportional to the volume. So Boyle's law is something which is supposed to be common sense. When you press the gas, its volume decreases. Okay, so Boyle's law. PV equal to constant. So how we get that? So basically, it's like, when you have inversely proportional, you can create a constant of proportionality again, like this. And then if we get PV equal to a constant, so that's why we have PV equal to constant over there. And of course, after that, we can create a formula which is P1 V1 equal to P2 V2. So that is the Boyle's law formula and its application. Charles' law. Charles' law, we have V proportional to T. So that means volume is directly proportional to the temperature in Kelvin. So imagine that the higher the temperature, you heat up the gas, imagine that, then the gas expands, right? So it has a greater volume. So gas expands. So again, when you have proportional, then you can create the constants of proportionality, which is K. So we get V equal to KT, and then we get V over T equal to constant. And then we can create a formula, V1 over T1 equal to V2 over T2. So this is Charles' law. And you combine Boyle's law and Charles' law, then you get an equation, which is P1 V1 T1, P2 V2 T2. Okay, so this is general gas equation basically. When we use this formula, right, the thing is the R is not there anymore. The R is not there. Okay? If R is not there, right, we are free to decide in terms of pressure, whichever unit. Okay? No need to do like just now, just now PV equal to nRT, right? That fixed already. Pascal must pair up with meter cube. Kilopascal must pair up with dm cube. Now, not necessary. For example, pressure, you use Pascal. Volume, you use cm cube. The other side, Pascal, cm cube. It is fine, It is fine to be like that. Okay? Only this PV equal to nRT, it fixed. It's fixed to either the first pair or the second pair because the R is there, 8.31 is there. This one, the R is not there, so you are free to decide whichever pair. So you can take pressure as maybe kilopascal, and then your volume as maybe atm, just fine, no problem. But temperature, you can't change to degree Celsius. Temperature must use Kelvin. Okay, now next one. Kinetic theory of gases. So we have first point here. They said Molecular movement causing pressure. Molecules of gas hit and rebounds off the wall of the container. So there is a change in momentum. Change in momentum give rise to pressure. Okay, so what is change in momentum? So let's do a revision here. Change in momentum is mv minus mu. mv minus mu is actually impulse. Impulse is ft. So when there is a change in momentum, then there is a force that come together. These are the idea of impulse. Okay, so and this force creates pressure, at the end, pressure is force over area, so it creates pressure. So third point, many impulses average to give constant force and hence pressure. Okay, so this is the physics way to explain why there is a pressure in a container with gas. So you have to explain this way, especially use the word change in momentum. Okay, and then force, then pressure. So remember the key words here. So now let's move on. Okay, next point on the right. From observation of a smoke cell under a microscope, the Brownian motion of particles, which is haphazard, random, provides evidence of movement of gas molecules. Okay, so what kind of situation is this? Brownian motion. A quick revision. So the scientist, Mr. Brown, put a cigarette here. So the smoke of the cigarette is moving in zigzag direction, meaning that the gas molecule is colliding in different way, showing that gas molecule move in random directions. So the circle that I draw is the gas molecule, which collide with the smoke particles and make the smoke particle move in zigzagging directions. So that is Brownian motion. Okay, now basic assumptions of the kinetic theory of gases. So we have gas contain large number of particles, negligible intermolecular forces of attractions. So that means no intermolecular forces or very weak. Volume of particles negligible compared to container. So that means the particle is assumed to be a sphere, right? So a sphere should have volume. So the volume is too small already. We ignore it, assume zero. Compared to the container, is a very large container, but of course its volumes is very big, and compare with the volume of particle, this is very small. So we assume zero. Collisions between particles are perfectly elastic. So when we say this, that means there is no loss in kinetic energy. No loss in kinetic energy. Kinetic energy remains. No time spent in collisions. No time spent in collision is what? So is imagine I give you two scenario. First scenario, let's say two hard stones collide. The second one, two soft balloon collide. Okay, the first case here, two hard stones collide. This is a case where there is no time spent in collision. So why? Because they are hard. When they collide, they will just rebound straight away. Okay, there are no time spent in collision here. It means the stone do not stick to each other for a particular moment and then bounce off. We don't have that kind of time, the time where they stick together and after a while it bounce off. We don't have that time. Okay, so this is where the first case, no time spent in collision. Number two soft balloons collide. So when the balloons collide, they stick together, then the balloons are flattenings partially for a short moment of time. Initially they are round shape, they stick together, then flatten off a little bit, and then after that they bounce off from each other. So it spends a bit of time for the soft balloon to stick together for a while. That is time spent in collision that mean. Okay, so that means the first one, no time spent in collision, but the second one, the second one, time spent in collision. So when I say no time spent in collision, it means we assume the ideal gas here is made of a hard sphere. Okay, so no time spent in collision. I write down. No time spent in collision happen to hard stone. So conclusion, that means ideal gas particles behave as hard sphere. Something which is hard, they don't flatten partially and spend time stick together. They don't have that scenario. So meaning that ideal gas is hard sphere. Okay, let's move on. I have to say this because past year question they asked before no? So now last point. Average kinetic energy is directly proportional to the absolute temperature. So meaning that absolute temperature is temperature in Kelvin. That means the greater the temperature in Kelvin, the greater the kinetic energy. Okay, so you have to memorize up all these assumption, and they will ask you to write a few sometimes, maybe 2 or 3. So you have to just remember at least 2, 3 assumptions here. The best is remember all. So let's move on. 3.4. 3.4 is molecular movement and pressure. So this part is deriving of formula, which is a bit hard actually. Okay, now let's see how we derive. Consider a cube of space with length L and a particle moving with velocity c. Okay, so which is something like this. As you can see the diagram here, a particle is moving in the cube with length L and with velocity c. Okay, I put it in 2D. Okay, I put it in 2D. Okay, in 2D. Imagine that the particles start from one side of the cube just now and move all the way to the other side of the cube. Okay, something like from the left surface of the cube, move all the way to right surface of the cube. So that's why in 2D it looks like this. from the left surface to the right surface. So they collide with the right surface and then they bounce off. Okay, so the bounce off and go back. Okay, now the distance traveled is L. The speed is C. The speed is C. Yeah? So let's say I assume going forward is minus C, going backward is C. Yeah? So I do so because I want to match with the information in the notes. Okay, so now you can see the notes now. Second point, when particle collide with wall, velocity is reversed. You can see minus C become positive C. Velocity reverse. And change in momentum is change in momentum. So you know change in momentum is mv minus mu. Okay, so m, your v is C, your u is minus C. So because of that, I can match with the notes and I get 2mc. So as you can see, the notes here, 2mc. 2mc, yeah? This is change in momentum. Distance moved by particle is equal to L plus L equal to 2L. So you can see that in this drawing. When they move forward, distance traveled L. When they move backwards, distance traveled is again L. So altogether, 2L. That is the total distance moved. Using speed distance formula, time between collision is t equal to, time is distance over speed, right? So time is 2L. 2L is the distance from here go to here and go back here. That is 2L. The speed is c. C, yeah. Okay, so we have many information already. We have change in momentum, 2mc. We have distance moved. We have times. And now, rate of change of momentum. Rate of change of momentum. Rate of change of momentum is change of momentum over time. Change of momentum over time is actually force. As you can see the impulse formula here, change of momentum is Ft. If you bring the T down, it becomes force. So force is change of momentum over time. Change of momentum we know is 2mc. We substitute on top. Time is 2L over c. We substitute at the bottom. Then we simplify. Then we get mc squared over L. So this is the force. So we have force now. Okay, this is the force because of a particle. A particle, that means one particle. The force because of one particle that collides with the container and bounce off. Now, using above quantity to find pressure. Pressure is force over area. So force, we know already, mc squared over L. We substitute on top. Area, this is where we talk about a square. A square is L times L. So the area is L squared. So simplify this, mc squared over L cube. L cube is volume. So we get mc squared over volume. We bring the volume to the left, then we get PV equal to mc squared. Okay, so we have done the first part in 2D. So all these are 2D until this point. Until this point are 2D. We 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 understand it based on the 2D situation. But in real situation, it is a 3D diagram. So we temporarily put 2D just to understand it easily. So in real situation, it is 3D. So we consider what to do with the formula. Now, consider n particles in 3D. Just now is one particle in 2D. So one particle in 2D. I write down first. Just now is 2D and one particle. 2D and one particle, we get all this information. What information? 2D and one particle. So we get PV equal to MC square. Okay, now in 3D, because real situation is 3D, and real situation is we have a lot of particles. It's not just one particle in the container, there are a lot. Okay, so n particle in 3D, hence the 1/3. So what are they talking about? Hence the 1/3. So I try to explain to you in this way. Imagine that in 3D. Okay, now in 3D, there are six faces. Six faces. Just now in 2D, we consider two faces only. Two faces, which is the surface on the left and the surface on the right. Two faces. Okay, so now in 3D, we have six faces. We have surface on the left, right, front, back, up, and down. So all together, six faces. Six faces. And because of that, the total area is, why we talk about total area. Okay, I write down first. The total area is 3 times. Total area is 3 times compared to 2D. Compared to 2D. Okay, so the reason that I thought about this is because you see our working just now. Pressure equal to force over area, right? Force over area. Our area, we take two faces only, we take two faces. But in 3D, it is not just two faces. It is 3 times greater, 3 times greater. So pressure, I write down, pressure equal to force over area. The area is 3 times greater. 3 times greater. So that's why if you do the same thing as in here, I circle in green color. So if you do the same thing as in there, you should have 3 times of the area, 3L square, 3L square, 3L cube, 3 at the bottom. So that's why the 3 is there. So that's why if you do the next one, you will have the 1/3. The 1/3 is there. Okay, 1/3. Okay, so PV equal to 1/3 MC square. That is one thing. But the other thing is, just now in 2D, it is one particle. And now in 3D, it has n particles. So we need to adjust for the mass as well. For the mass, let's say I use red color again. The mass just now is m, and m. That is for one particle, the mass of one particle. Now it is not one particle anymore, it is n particles. So the m here is now nm. The number of particles multiplied with the mass of one particle. So we get the total mass, nm, nm. And this one become nn. So that's why if you look at the PV equal to MC squared just now. Now it become PV equal to 1/3 nm c square. You can see here, PV equal to 1 over 3 nm c square. But the c looks different also. Why? Because in real situation, right, the gas particle move with different kind of speeds, you know. If you still remember chemistry, there is a Boltzmann distribution. So they move at different speed. So because of that, we put this special symbol to show that this is the average speed and we square it. And after that, this is the formula in 3D. Okay, in 3D, this is the formula, and we have another versions. Okay, so the other version that we have here is P equal to 1 over 3 rho c square. So rho is density. Rho is density. So imagine that density means mass over volume. The mass is nm because I have to consider many particles. So nm over volume. Nm over volume, how we do it? So imagine you have this formula now. You bring down the v to the right hand side, and m over v is rho. So that's how we get that formula. Now, last point, mean square velocity c power 2. Mean value of the square of the velocities of the molecules. Okay, so mean square velocity. Yeah, you know, particle move at different speed. So in average, we call it. In average, we don't have square, right? The average speed is like this. The average speed is CRMS. What is this? This is the average speed. Like what I said just now, there are so many particles. Their speed are different. Some are fast and some are slow. So the average speed, we call it root mean square. Root mean square speed. Root mean square speed, which is the square roots of c power 2. The square roots of that. So if you square it, then we call it mean square velocity or mean square speed. Okay, you can also call this mean square speed. Mean square speed is already power 2, and the one before power 2 is root mean square speed. So be careful lah.